weights. But the problem of this is you are going to add a lot of connectors. Do you remember in the cross four-way stop sign case, we will need only 8 links and 1 node to model one intersection. But if we use link connector, we are going to create 12 new connectors. And this will bring 3 more nodes and 12 connectors. And that would mean the amount of time will be doubled, or more than doubled. So this is not the best solution, but it's already a feasible solution. And I'm not going to talk about the solution of this today. But you can pay some attention to it when you read the papers. The next problem is fast route planning. Let me give you an example. For Western Europe, the network consists of 18 million nodes, 43 million links. For this large number, can you estimate for a common query in Western Europe using pure Dijkstra algorithm, how much time it will take? Anyone gives an estimation? How much time does it take for Western Europe based on this large network only using Dijkstra? Any example? Any guess?
More than 10 years.
10 years?
More than 10.
Okay, another guess? The truth is, using the fastest workstation 2 years ago, it only takes 5 seconds. So you see the computing power nowadays is very, very big. 5 seconds. 5 seconds is acceptable when you are just calculating one shortest path. But you cannot ask Google to use it, because Google is receiving a lot of concurrent queries. And you cannot use it in transportation engineering or traffic assignment, because you have to calculate for many travelers, right? So it's still too slow. And the USA network consists more nodes and more links. So there are some feasible solutions, but don't give up. There is hope. I will introduce very soon. First one is called bidirectional search. The second thing is the ultimate solution called hierarchical. This is the one that Google is using. All these things, all these GPS things are using. We reduce the time complexity to almost 0.1. See, almost 0.1. How can you imagine that? I'm going to introduce this to you. But before that, let's talk about time-dependent algorithm. The formulation is very simple. For each link, travel time is equal to delay and base travel time. And delay is function of time, and it's always positive. It has almost no difference. The only difference is in time-dependent algorithm, the weight is travel time, and the weight is dynamically calculated. See this example. The same example, 3 nodes. You arrive at node A at 8 p.m. And at 8 p.m., starting at 8 p.m., you can then calculate the travel time from A to C and A to B using the travel time function, right? Correct? If you already know you will arrive here at 8 p.m., you will then use the link delay function and calculate when you will arrive at B, you will arrive at C. And we can still confidently say if you arrive at B earlier than arriving at C, AB will be the shortest path. Because you arrive at B at A6, if you go along AC and go anywhere else, you will come back to B only later. In another word, no matter how congested the link is, you come here earlier, you exit earlier. So in our common sense, if we hear that link is very congested, we may consider go there later. But you arrive earlier, you exit earlier. It's very logical, right? Think about this. So the link is the first out facility. Understand this? So the only difference is after calculating this thing, you add B to the shortest path tree. Then you start calculating these weights from 806. So these weights are dynamically calculated, but the tree generating procedure is the same. Understand? Another thing is called bidirectional search. So we want to go from start point to the target. We use two computers. One computer starts generating a shortest path tree from this node, and the other computer using a backward graph, which which is using the same weight as the forward graph, maybe negative, and is searching backward. So there are two computers or two processors, each of which is calculating a dextron. And if these two trees meet each other, then we find the shortest path. But this is a heuristic, according to what I understand. I may be wrong, okay? I have emphasized I may be wrong. This is a heuristic. I'm going to give you a counterexample. But let's first let's estimate the time complexity. So you see, ideally, this tree will form a shape like this. Maybe it's a circle. Let's say it's a circle. So it's creating a tree in a circle. If I am to create the path only using one processor, I have to search a big circle whose radius is this. Right? So I have to search a big circle. The radius is from this to that big circle using one processor. But if we are using two processors, we are doing simultaneously two searches, and the diameter, and the radius also will be reduced to half. So originally, we have to search for a circle that is almost equal to d, which, let me say it again. So originally, we have to search this circle. Now we only have to search this circle. So if the original search time complexity is O n log n, then what about this search? This will be squared, right? So this will be the new time complexity. If you understand this? And because these two things are being done simultaneously, the time complexity you can only, for the time complexity, you just use one of them. This is an example showing you the reduced search space. This is starting node, this is end node. If we use dextron, these these black lines, black links, are the links that have been included in the minimum path tree, shortest path tree. So you can see a large tree has been created. But if we use bidirectional, we only explore a small area. So that shows the reduced search space, and it's almost 1/4 of that.
That's German.
However, I have a counterexample. So for this one, if the trees meet, then we have a shortest path tree from this one to the meeting point, and we have another shortest path from the target to the meeting point. We know that this is shortest path, this is shortest path, but does that guarantee the combined path is shortest path?
No.
No. So here's a counterexample. Let's say we have one machine calculating from C, one machine calculating from A, and there is a shortest path tree, DC and BC. So shortest path tree, right? From C to D and C to B. These are two shortest paths. And from A, this is a little slower than that computer. So we only we'll only get one path in the shortest path tree, which is AB. Then we say these two shortest path trees meet. So this is shortest path, which is 10 plus 1 equal to 11. But there is another shortest path that has not been explored, and the path weight is 10. So I would say that this bidirectional search is heuristic. The ultimate solution is called highway hierarchy. The basic idea of highway hierarchy is to compose or create a hierarchy, include several levels, like in this example, L levels. The level 1 is the original graph. Then level 0 is the original graph. Then level 1 is computed based on level 1. All the nodes in level 1 are nodes in level 0. In other words, in level 1, the node set is a subset of the original level, but the links are not. So with ID of level or number of level increasing, the total number of nodes is decreasing. So level L has the least nodes. Okay, I'm giving you an example. Now, let's talk about bypassing a node or removing a node. So this is a network. We want to remove this node A. But if we simply remove it, we lost this shortest path, and we lost this shortest path. So what we are going to do is to remove this A, and at the same time, create a new shortcut between C and D. A new shortcut between C and B. Okay, here we are using the undirected example. So we don't consider direction, okay? So we remove A, we have to add two shortcuts. By doing this, we are reducing the amount of nodes in the network. And as I introduced, with O n squared, if you reduce this n, you will get very efficient algorithm, or very small runtime.